Welcome. In this video we talk about enums. In Rust, enums are not just enumerations like in C++, but the full power of algebraic data types, that is tagged enum and union types, is behind this concept. We will see the rest in the examples. We start simple by just using enum as an enumeration type. If you declare an enum like this, you can just give multiple values. And then you can use the enum just with the name of the enum and two colons and then these values. Here I have a variable of type E. Here I have a mutable variable. You can print them with a debug notation because I used the already known derived debug. And you can reassign the variable if it's mutable. Let me see how this runs and prints. As expected, you see value 2, value 1, and value 3, because down here we have assigned value 3 to the second variable. But enums can do a lot more. Here I use the enum as an algebraic data type, or in other words, as a kind of tagged variant. Here the type E can either be a number, in which case it would store a single integer, or it can be a text, in which case it stores a string. The data type automatically remembers what it is. For example, here I form a number. In the constructing case here, I have to just use an integer. And here I construct it as a text. You see, I use the name of the variant, and in brackets I use the actual argument for the type. And as you can see here, E2 is first a text and later a number and is always printed correspondingly. Here it's printed as a text and here it's printed as a number. In this example, that there is quite a few more possibilities. For example, here, one of the variants is a tuple, in which case I just use the tuple notation here. And the other variant is a user-defined struct, such that the text is here hidden behind the struct A. Furthermore, I tell you how to use these things, such that you can write them more compactly. So, for example, here I construct an element of type A with the usual notation. Then I form a type E, but this time in the tuple variant with two integers. And here I form it in the text variant with an object A inside. Remember, things are move semantics by default. Let me try to run this. Very well. It's printed exactly as you would expect it. So you can have variants which are your own structs, and you can have variants which are tuples. Enum types can be arguments to function exactly as other types. So for example, here I have a function which is a type E. I could have used references or mutable reference exactly as you know it. But then I don't have to specify which variant it is. So the function can either take a tuple or a text. And this is demonstrated here. I call it this time with a text. Run this. Here in F we have a text. But it becomes only really convenient if you can actually distinguish what type of thing you have. And this is where the match operator comes in. For example, here I have the same program with the same setup, but my function, which takes an E-type argument, now reacts to what it gets. I use the match syntax here, and if I match E to be a tuple, I use this notation here, and as you can see, the variables x and y are locally bound to the contents of the enum. So for example, x in here has type U64, and here as well, because the tuple consists of two 64-bit integers. And therefore, within the block of this match here, I can use x and y as if their type would be really the parts of the enum. And down here, this a here is automatically of type struct A, because I have matched here for the text variant, and the text variant has an a here. So down here I call this thing twice. Once I call it with a text, and the second time I call it with a tuple. Let's see how this behaves now. First time f says f got a text, and it writes the a type, and then it says I got a tuple, and it writes the two values x and y. This match construction here, where you match and assign automatically to parts of the construct, is a kind of destructing assignment. It doesn't take apart the enum, but it binds variables to parts of it, which is very convenient when writing code with algebraic data types. Enum types can have methods, and they are implemented basically like for struct types. So I say impl e, and then I define a method, here f. If I use the word self, I refer to the type itself. So this here takes a reference to e. I can then use the code as I would by using the self word here for the argument. And when it comes to calling, I now can call the method f with a dot notation on the object of type e. So here I have a method call and another method call. So this program does the same what it did before, let me see, but with method syntax. I want to finish this example by mixing everything. The one thing I haven't mentioned is that you can also embed a struct directly into the enum type, like this here. Rather than putting a round bracket and a struct name here, I can directly use a curly bracket and put components as I would for a struct. In this case, I have to construct it in this way, also with a curly bracket, and that can be very convenient. Note that I can mix empty things without data, or with a single type, or with tuples, or with structs in one and the same enum, which is very easy, very convenient when modeling data. Let me show you how to run this. There's a warning because I've never used these fields, but never mind. I get the empty type, one value, a tuple, or indeed a person, like this here. For me, these algebraic data types and the enums and the convenience to work with them is one of the major benefits of Rust. The match syntax is very convenient and makes for very easy data modeling. I hope you enjoyed this video, and I'll see you in the next one.